I want to look at another example. This is problem 4.4-8, and the circuit looks like this. We have a capacitor, a resistor here, 1 ohm resistor. This is a 1/5 farad capacitor, 1 ohm resistor, a 2 ohm resistor here, a 1 ohm resistor here, another 2 ohm resistor here, and then a 1 Henry capacitor, 1 Henry inductor. And we've got a DC voltage source that's actually switched on at t equal to 0. So I can model that as 100 U of t. And we're interested in the current from our voltage source, which we'll call Y of t. And we're given the initial conditions. The initial voltage across the capacitor is equal to 10 volts. That's with this polarity. And then the initial, this is across the capacitor, the initial inductor current at 0 minus is 0 amps. Okay. So transforming into the S domain, let's use a different symbol for my voltage source. It becomes 100 over S. My capacitive impedance, it's C is equal to 1/5, so 1 over SC will actually be 5 over S. And then due to the initial voltage across the capacitor, I have to include a series voltage source of 10 over S. Bring down this 1 ohm resistor, this 2 ohm resistor, another 1 ohm resistor here, this inductor, because the initial current through it is 0, the equivalent model is just the SL impedance, and since L was 1 here, I'm left with this. Could use mesh analysis here, and I'm interested in this current Y, okay. Or nodal analysis. I'm going to just take a different approach. I'll find the equivalent impedance looking to the right into this pair of terminals, and so I can write that as, I can see that is equal to, we've got this 1 ohm resistor in parallel with, I'll have this 2 ohm resistor, which is would be in series with, I see the 1 ohm in parallel with the inductor and resistor in series of S plus 2. So notationally I can write the circuit out, an expression for the equivalent impedance algebraically out like this. I'll combine, do this parallel combination. I'll just use the product over sum formula. So I'll have 2 plus the product would be S plus 2 times 1 over the sum S plus 2 plus 1 will give me this. Okay. And now I'll combine these over a common denominator, determine brackets here. So here the common denominator would be S plus 3, and then I'll have 2 times S plus 3 plus S plus 2. So this becomes 1 in parallel with, I'm going to have here 3s, and I'll have 6 plus 2 or 8 over s plus 3, and then finally combining my own 1 ohm resistor here in parallel with the equivalent impedance of the rest, the 3s plus 8 over s plus 3. You can do product over sum here and then do a little algebraic simplification, and the result for the equivalent impedance is 3s plus 8 over 4s plus 11. I'm actually going to combine the two voltage sources here into a single voltage source. The current is actually going through both of them, and then add this 5 over s into this equivalent impedance to actually come up with a total impedance, ZT, which is the capacitive impedance, plus the equivalent impedance that I had looking to the right, 3s plus 8 over 4s plus 11, and combining these over common denominator and doing a little algebra. I get 3s squared plus 28s plus 55 all over s times 4s plus 11, and then combining the two voltage sources, 100 over s minus 10 over s. It's nice, they're already over a common denominator. The minus here taking into account the polarity of the second source. And so the total current is just, from Ohm's law, this is the current through the voltage source, is just VT over ZT. Okay. And here I'll have the 90 over S. Take the reciprocal of this, the s's will cancel. I have 4s plus 11 over 3s squared plus 28s plus 55. And before I do a partial fraction expansion, I want to make sure that the leading coefficient on my highest order term in my denominator is 1, so I'm going to factor out that 3. That'll give me a 30 in front, 4s plus 11. Then I'll have s squared plus 28 over 3 times s plus 55 over 3. You can factor this out. It actually has two real factors of 2.811 and 6.523. The partial fraction expansion actually becomes minus 1.972 over s plus 2.811, and then plus 122.0 over s plus 6.523. And now I'm in a position to find the current in the time domain, y of t. Take the inverse transform of this first term, I'll have minus 1.972 e to the minus 2.811 t, and then plus 122.0 e to the minus 6.523 t u of t. You'll see here that y of t is actually going to go to 0 after these terms decay away. They're decreasing exponentials. So eventually y of t will become 0. We look back at the original circuit, we had a capacitor in series with our voltage source, so it's just what we would expect, that initially after our voltage source turns on, and we also have an initial voltage across the capacitor, there's going to be some current flow, but then once things settle down, because we've got a DC source in series with that capacitor, we would expect our current to eventually go to 0.